Logic modeling is one of the areas that helps in that direction. And we also support new features for the futures, in particular for smart grid applications. Thank you.
Thank you. I think we have time for maybe one or two clarification questions, short clarification questions. Okay, if not, let's move on.
It was clear.
Mark?
And good afternoon, and welcome to the new Goose. Life is changing as we once knew it. Goose, by the way, is an acronym. So the 61850 you've heard provides some very unique capabilities that no other protocols have. Specifically, early on in the development of 61850, the need for device to multiple device communications was identified. The solution to this became known as the generic object-oriented substation event, or the GOOSE. In parallel with that, as the process bus was developed, the ability to send sample values from one data source to multiple other data sources was identified. Both of these original implementations were Ethernet-only data frames, meaning there was no Internet protocol, there was no TCP, there was no UDP, just raw data mapped directly into an Ethernet data frame. Like all good protocols, however, as time moves on, the requirement for routing this information starts to develop, and that's what we have in this case here. And where do I point this?
Just the up down on the keyboard.
On the keyboard? No, don't use this. Okay.
You can use the laser.
Specifically, what's been happening today? So the driver for this has been SynchroPhasor specifically. In today's SynchroPhasor environment, you have one source, and that one source has to develop multiple remote connections. And it's one connection to each remote. There are some multicast implementations available today, but the standardization is lacking as we go forward. We'll skip broadcast here. Where we want to head is a multicast IP solution, where I have one publisher at one location, and that information that this publisher has wants to go to multiple remote locations and has to be routed through a network of routers in the utility infrastructure, or even in the outside world, as the case may be. The other driver were issues with the existing SynchroPhasor standard, which is known as C37.118. Right now, 118 does not define any security. And the multicast definition doesn't exist either. It just says you can transmit it. And there have been vendor-specific implementations at this stage. The dataset configuration tools are vendor-specific at this stage, and there's no standardization in the data names. And some other issues. The vision that was proposed it actually has a name. It's called NASPI Net, which is the NASPI network. And the vision for NASPI Net was one of having a device publish information and have many, many devices, other devices, receive the information. And part of this publishing is also the creation of the data set, having a standardized way to create the items that are going to be published in a particular data set. What happens today with both the goose and sample value messages? When a goose or sample value messages hits a router, there's no IP, no TCP. The router does not know what to do with these messages. So today, they go into the bit bucket. Clearly, what is needed is the ability to route this information through the network. And this has now been defined. This is what 90-5 is all about. It defines the mechanism for allowing the goose messages and specifically the sample value message to be routed through a network. Needs, the message should be routable. It should be multicast, so I can have, again, one-to-many. The message should be able to be authenticated. It should be able to be encrypted. Should be able to include large message sizes. So if I'm sending all the data from a given utility, I can encompass this in one message going forward. And obviously, when you authenticate and when you encrypt, you need to be able to manage the keying. A technical report has been published and accepted, and voted and accepted in the IEC. It's typically known as Part 90-5 and is known as the use of IEC 61850 to transmit synchrophasor information according to IEEE C37.118, which is the existing synchrophasor standard. In fact, specifically what happened is the IEEE sent the synchrophasor standard to the IEC for dual logo. And the IEC came back and said, no, 118 does not meet the communication standards that are presently defined by 61850. As a result, the synchrophasor standard was split into two parts. The first part is the measurement part, which defines how to create a synchrophasor. And the IEC is actually very much in alignment with this part one. Part two was really a duplication of the existing synchrophasor communication protocol. This has now been paralleled by this document here, by the 90-5. So this was now in the 90-5 is synchrophasor communications in coordination with the tenets proposed by IEC 61850. So we needed a name for this new protocol. I did propose the Network Object-Oriented Substation Event, or the NOOS. The chairman got hung up on it. So subsequently, the working group, being a little more rational, came up with the new names, which is called RGOOSE for the routed goose, and RSV for routed sample value. So this is the new name of these two new routed devices. I'm going to start here. So what does 90-5 do? Well, we still have information that we want to send. We have a protocol data unit. We have a goose message. We have a sample value message. What 90-5 does is now encapsulate those data units around a UDP IP wrapper. So what you see in this picture here is something called an IEC header. This IEC header adds 3 elements to these data packets. The first element is what's called the quality of service. This is Ethernet. This is IP. It's really it's Ethernet quality of service, otherwise known as the 802.1q IEEE standard. And this does 2 things to the message, to the Ethernet data packet. Number 1, on switches, it provides priority switching for this message through an Ethernet switch. Number 2, it provides the ability to put a VLAN tag on the message coming out of the device. So it gives the message coming out Ethernet priority and Ethernet switching through the Ethernet switch out of the device. The next part is it adds in an IP layer. The technical report says you can use either IP version 4 or IP version 6, and it has a complete definition on how these two layers are to be mapped. And I'm going to go into one or two of the specifics as we go forward. And then lastly, it defines the transport layer as UDP. UDP does not repeat any messages. So UDP is a complete pass-through layer. All it does is says, here's your data. If you get it, fine. If you don't get it, that's also fine. So there is no guaranteed delivery of data. However, as you're going to see in a couple of slides, there is the ability to repeat data sets. So we get reliability through message repeat. And then lastly, so this is what's tagged on to these existing messages. And that is the primary difference. So these messages now become routable through any standard routing network. In addition now, the protocol adds on information for the handling of security. So baked into this new profile is complete end-to-end security. And as we're going to see in a minute, security in this implementation has three components. Number one, it has the ability to share a key between the publisher and multiple subscribers. Since this is multicast, each subscriber has to know the key that is being used to lock the message at the publishing end. So it defines the complete key sharing information. You'll see it in a minute. It also defines the ability to authenticate the message and the ability to encrypt the message. What you see here is a mechanism for sharing the key between the publisher and the multiple remote subscribers. Down here is this thing called Payload. And what's unique about 90-5 is this payload is composed of multiple data sets. And what's interesting now is this now provides a whole new paradigm on how I can send synchrophasors. In the past, synchrophasors with the 118 protocol had to be time aligned, or otherwise you lose the timing information. With 90-5, I can take a single PMU with a timestamp and roll it into this payload. I can have multiple PMUs, each one with its own timestamp and with its own data set rolled into this payload area and deliver it to a remote location. So now I no longer have to have a wait time for my SynchroPhasor. I can immediately collect the data in what was called a buffer time in 61A50 language and immediately send out the message. So the payload is defined. Now 61A50, you've heard about this thing called process bus. The payload consists of data sets as defined by the process bus section of 61A50, which is known as 9-2. And the payload consists of a header and a data set. I'm going to point out that in the present implementations, the data set for this 61A50 implementation is identical to the data set for a 118 mapped device. So this makes it easy to transition from existing 118 implementations directly into 90-5. implementations. In fact, the configuration file for 118 can be used to configure the received data set for 90-5. I won't go into detail here, but suffice to say, in doing the mapping from 118 into 90-5, it made sense to put together what is known as an implementation agreement. And this is very similar to, well, the implementation agreement says, if I take this data here, how does it get mapped into a 90-5 data set? So this document exists. It is now going to become part, we just started a new working group in the IEEE, and this document is going to become part of that working group and will become a published report, a published IEEE report on a recommendation to do the mapping from 118 into 90-5. And these are some of the items. For example, identification of the data frame, how to create the name. In fact, there's a one-to-one mapping between the naming in 118 and the names as they get mapped into a 90-5 implementation. Also, there is something 61A50 defines something called a refresh time in the data set. And we've made the one-to-one mapping that says the refresh time is going to be the SynchroPhasor timestamp as per C37.118. So again, a one-to-one correspondence between 118 and 90-5 moving forward. The status word is included, frequency, rate of change, synchrophasors, and analog, even in the same sequence as they are presently transmitted in a 118 data frame. Now, this is another unique feature that comes in with 61A50. In 118, if you transmit, so how do you get data reliability? When you transmitted a 118 frame, you had two options. You could send it as a TCP frame, or you could send it as a UDP frame. Obviously, if you send it as a TCP frame, on loss of a packet, the TCP would request a retransmission. However, as data rates started soaring into the 120 messages per second rate, TCP starts becoming untenable, because if you do have a large block of data that gets lost, your TCP connection crashes because it cannot buffer enough information for a long loss of data. So UDP starts becoming the operative application for the faster rates. UDP says you lose data, such as life. With 90-5 now, there is the ability to have multiple data sets in one message. Now, in this case here, what we're looking at is sending the term in 61A50 parlance is Application Service Data Unit, ASDUs. These ASDUs is one time instance of a set of synchrophasors. What is defined in the technical report is the ability to send the most recent data set, as well as 1 or 2 or 3 or n older data sets. The implementation agreement right now makes a recommendation of the ability to send the most recent data set as well as 3 older data sets. So if that means if you miss 1 or 2 or 3 messages, you lose nothing, because when the new message comes in, it contains any lost data. For losses of more than 4 data sets, you are out of luck, and you have to, and the group is looking at other mechanisms to make up larger losses of synchrophasor data. We talked about priority on an Ethernet switch. That's one level of priority. It turns out, however, that the Internet Protocol, IP, also supports priority routing. Specifically, there is 1 byte in the IP message header called the differentiated services byte. And this byte allows me to set a priority for routing of information. So if you have your routers configured for routing priority, when a SynchroPhasor message comes into a router, it will get priority and be the first message routed through the router. The goal here is to minimize latency of SynchroPhasor messages through a network, and this provides one of those mechanisms. I'll just mention in passing, in the 118 standard, there was the ability to set the time base for the fraction of a second. The message had the ability to have up to 24, you could set anywhere from 1 bit to 24 bits of resolution in the time base. Going forward, to match the implementation with 61850, the time base shall always be now 24 bits going forward, which means that you will be able to resolve the timestamp of a SynchroPhasor down to 59.604 nanoseconds with a complete 24-bit time base. So benefits of the multicast versus the unicast. So let's say I have a phasor data concentrator, and the phasor data concentrator is sending SynchroPhasor messages to 3 regional control centers. Today, I have to have 3 times the bandwidth from that phasor data concentrator to my 3 remote points. Going forward with a multicast solution, I send out 1 message to the first router. This first router now knows that it has to send this message to 3 different locations, to green dot number 1 up top here, to green dot number 2, and then on to the next router. And the next router is smart enough to know where to send that message to. How does the router know where to send the data? There's a very interesting new protocol that must be implemented at the client head end called the Internet Gateway Management Protocol, or IGMP. IGMP is the protocol that establishes the path from one publisher to one subscriber. So this subscriber here says, I want to receive messages from the video server in this example here. So it sends a message to the router closest to the video client. This is known as the last hop router. And the message says, please find the video server for me. The last hop router then uses a special routing protocol called Protocol Independent Multicast, or PIM. This routing protocol, which is available on all routers, then establishes the path from the closest router to the router next to the server. And these routers now remember the path of where the data is to be sent. There's an interesting follow-up here, and that is, if no one's listening, why send data? So how do you know if the video client is still listening for data? Periodically, this router will send a message to the video client. And this is really a SynchroPhasor client. It's cut and paste. So the message is, are you still listening? If the client doesn't respond back, the router cancels the connection. So it does not waste bandwidth and doesn't send data unnecessarily. What is going to feed the information in a 90-5 data set? as I mentioned in one of the gaps in 118, there is no standardization on the data names in 118 at this stage. 61850 does not have that issue. 61850 has explicit names for all synchrophasor information. Specifically, we find these names in something called an MMXU, which is a measurement unit, and something called MSQI, which is also a measurement unit for the sequence voltage and current quantities. So out of the measurement unit, we get phase voltages and synchronized phase voltages and synchronized phase currents. In fact, I've typically been referring to these now as the synchro logical nodes. Specifically, what's different about these? The logical node has something called a calculation method that says, how is the data in this logical node calculated? The 90-5 technical report defines a calculation method known as a P class or as an M class. So going forward, a synchro logical node, for example, this one here says M60. The implementation agreement says that M indicates that this logical node is a measurement class logical node. The 60 says that this logical node is reporting data at 60, is configured to report data at 60 measurement sets per second. Obviously over here, P120, P indicates that this logical node is designed to send out P-class synchrophasors at a rate of 120 measurements per second. So going forward, your devices that support 61850 will also have logical nodes that can be even read by a client. And the client at any instant in time will be able to pull up a synchronized phasor measurement along with the synchronous time stamp. We'll skip this one here. What does the future hold as we migrate towards complete 61850 implementation? You heard Ralph mention earlier that there is this concept of a capability description, IED capability description file. So if I go to Vahid and say, Vahid, what do you know? Vahid can tell me everything that he knows in a file format. Same for a relay. So when a client goes to a relay and says, who are you? The relay can dump a file which describes every piece of data inside of that device. So as a phasor data concentrator now, we can create the concept of a proxy server. This proxy server is an image of all the elements available inside every PMU inside the device. This is equivalent to what is known as a CFG1 file. CFG1 is a term defined in the 118 standard. And the configuration 1 file says, what is the total ensemble of data available to be mapped into a synchrophasor data frame. And this is now automatically available through this ICD file definition concept. In the implementation agreement, the agreement says we're going to map data into the data set in the exact same order as the data was mapped in a 118 data frame. So what we see is the first data item in a data set is what's called the stat or status word. What is the status of this PMU that is sending data? Then we have the PMU 1 data, PMU 2 data, so we can still aggregate multiple PMUs in one single 90-5 data frame. Each individual PMU would have the stat word followed by synchrophasors. Now going forward, all synchrophasors shall be transmitted as 32-bit floating point numbers. And only the polar format is available going forward. There'll be no more, the 90-5, 61850 does not support rectangular format for complex numbers. It only supports polar format, so there will be a magnitude and an angle. Frequency will be a float 32 number. Rate of change of frequency be a float 32. Any analog values mapped into the data set will be 32-bit floating point numbers. And the one